point the presentation stopped?
A bit before that.
I think slide 7. What? This one, 8.
Yeah.
Yeah, this one.
Okay. Okay. So so yes, here I was explaining that every state associated to a spin network graph can be seen as a map between the bulk and the boundary degrees of freedom. Here we see there is a space associated to a certain graph. It is given by the tensor product of the intertwiner space associated to the vertices and the representation space associated to each boundary edge. So the idea is that given a certain state associated to a graph, we can feed the intertwiner degrees of freedom with a certain input state written here, and the resulting state, so after the imposition of these intertwiner correlations, is a state that lives on the boundary. So this shows that every state can be seen as a map from the bulk to the boundary, a map that acts as follows. So as I said, we have a certain state for a bunch of intertwiners. Once we impose on the graph state that correlation between intertwiners, we are left with a certain boundary state. So this can be generalized to the case in which we have a spin superposition. Note that in the general case there is no factorization between bulk and boundary degrees of freedom, because the intertwiners are recoupling spins which live on the boundary, which can also live on the boundary. So in the fixed spin case, the factorization is natural, but in the general case, it is not. So we can, however, we can still consider every state as a map of this kind, but by embedding the state in the tensor product of generalized bulk and boundary Hilbert spaces. Of course, the difference is that we have a strict correlation between the input and the output. So the only non-vanishing components of the map are the one in which the boundary spins are a subset of the whole set of spins attached to the graph. Now, so we have this. We have seen that every spin network graph represents a map from the bulk degrees of freedom to the boundary degrees of freedom, and we want to study the properties of this flow of information. In particular, we ask if it is an isometry, so if the map satisfies this condition. Now, the basic observation here is that we, instead of directly probing this condition, we can study the reduced bulk state of the corresponding spin network graph. Why? Because every graph state, the graph state can be also seen as the result of applying the map to just 1/2 of 2 copies of the bulk state, maximally entangled bulk state. So we have a sort of dualism between the state and the corresponding map. And when we write down the reduced bulk state in terms of the map components, we see that the condition that the back to boundary map is an isometry is equivalent to the condition that the reduced bulk state is maximally mixed. So it maximizes the entropy. So our goal is to compute the entropy of the reduced bulk state for spin network graph and see if it is maximally mixed. So see if the corresponding bulk to boundary map is isometric. Now we focus on the class of states I introduced before, so tensor network states, but with the further assumption that the wave functions associated to the vertices are picked randomly according to the uniform probability distribution. So here we have the state. Every wave function is a random wave function. Here I write the density matrix for the state. Since this, so I'm going to show that the average Rani entropy of this state can be mapped to the evaluation of the free energy of an Ising model defined on the graph, on the spin network graph. But here I'm showing the technique in the general case in which we are probing a certain region A of the boundary and omega of the bulk, because this technique, we will use this technique also for the second part of the talk. So here I'm not focusing on the specific case now of the bulk entanglement entropy, but of a general region of the graph. So the idea is the following. The first step is to apply the replica trick, the so-called replica trick for the Rani entropy, which allows to write the entropy as the logarithm of the ratio of two quantities, zeta 1, zeta 0, that involve two copies of the graph state. And then in zeta 1 we have this operator, which is an operator swapping the two copies of the Hilbert space of the region we are looking at. And this swapping on the two copies allows to perform the partial trace for the entropy. Now we look at the average Rani to entropy, since we are assuming a random distribution of the vertex wave functions, and we also consider the regime of high dimensionality of the involved degrees of freedom, so that the average entropy is given by the logarithm of the average values of the zeta 1 and zeta 0 quantities. So here is the form that zeta 1 and zeta 0 take. So two copies of the link states that implement the connectivity pattern, two copies of the vertex wave functions on which we average, and then the swapping operator. And here is how this calculation translates to an Ising model. So here I just give you the general idea, not the details. So the idea is that from the average over the vertex wave functions, some Ising spins arise, one for each vertex, that can take values plus or minus 1. And from the swapping operators, we instead have the so-called pinning fields, but just spins. So a set of spins for the boundary, which take value -1 only if the edge is in the region A we are probing, and the bulk spins, which take values -1 only if the vertex, the corresponding vertex, is in the region omega we are looking at. So boundary spins for controlling the boundary region we want to probe, and spins called bulk spins attached to the intertwiner. And so these quantities are turn out to be specific cases of a partition function of an easing model, and the easing action, after deforming this trace, the easing action turns out to be the following. So we have interaction between easy spins, and the strength of interaction is proportional to the logarithm of the dimension of the link connecting them. Interaction between easing spins and corresponding easing spins that live on the boundary and the corresponding boundary spins, and the same for the intertwiner ones. Then we can define a free energy for this model, and so the Rani entropy is finally given by the difference between the free energies corresponding to the zeta1 and zeta0 partition function. Note that since the zeta0 quantities has just the identity operator, not the swapping one, in zeta0 all pinning fields, so boundary and bulk ones, are equal to +1, and while in zeta1 we are flipping down the boundary, the pinning fields in the region A and omega. So in the end, the average Rani entropy is given, corresponds to the energy cost of flipping down the spins in the region we want to compute the entropy of. So now we are back to the checking of the isometry for the back to boundary map. So as I said, we want to check that the entropy of the bulk, under which conditions the entropy of the bulk takes the maximum value. So in this case, here in red, we have the spins, the pinning fields attached to the boundary. In green, that for the bulk degrees of freedom, namely for the intertwiners, and in black, the easing spins. So for the case, for the zero configuration, as I said, all pinning fields point up, and so the easing configuration that minimizes the action, which is the interesting case in the high dimensionality regime, since the partition function is dominated by the configuration that minimizes the action. So in this case, the configuration that minimizes the action is that in which also the easing spins point up, so get aligned with the pinning fields, and the free energy is 0. So we are left with the computation of the free energy for the zeta1 partition function, and in this case the bulk pinning fields are flipped down. Now in the homogeneous case, so in the case in which all spins on the graph takes the same value, it is easy to see that the logarithm of the dimension of the spin plays the role of inverse of an easing temperature. And so we have that the action can be written in this way with an easing Hamiltonian. And so there are two, we can consider two extreme regimes. One in which the strength of interaction with the intertwiner, so for the intertwiner degrees of freedom, is much stronger than that for the links. In this case, the pinning fields are dominant, and so the easing spins get aligned to them, and so point down, and the only contribution to the entropy comes from the misalignment between easing spins and boundary spins. And so the entropy is given by this quantity. So the number of edges along the boundary times the weight of the interaction. In the other case, in the case in which the strength of interaction for the with the boundary spins is much stronger than that with the bulk spins, then the easing spins get aligned with the boundary, and so the contribution to the entropy comes from the misalignment between easing spins and bulk spins. And in this case, we have that the entropy is maximized. So the result of this observation is that the isometry condition for the math can be translated to the requirement of stability of the configuration in which all easing spins point up. Now we can rewrite this condition in terms of the region X here in which the easing spins point down. Here we have a picture that in yellow shows the region in which the black easing spins point down. And so the stability of this configuration means that this inequality must be satisfied whichever spin down region we take. And what we can observe is that in the case of a graph, we are in the homogeneous case, so all spins are equal to the same value. If the vertices are 4 valent vertices, which is the case in which the dimension of the intertwiner is equal to the dimension of the link, this inequality is violated because we have that the boundary, the number of edges on the boundary has to be greater than the number of vertices in the bulk, whichever region we take. But this is not true for the whole graph, for example, because we are assuming that every vertex has at most one boundary link. And this means that for this graph, for this class of homogeneous graphs, the flow of information from the bulk to the boundary cannot be an isometry. In the more general case, in which the spin assignment is general, every pair of spins interacts with a different strength, which is proportional to the corresponding link. So now we still can map the isometry condition to the requirement of stability of the all-up configuration, but in this case we rewrite the condition by introducing this delta parameter, which is a parameter that controls that quantifies the inhomogeneity of the spin assignment to each vertex, because for each vertex this parameter is equal to the difference between the maximum and the minimum spin associated to that vertex. And what we can observe is, so in the case in which this is 0, we are back to the homogeneous case, so we cannot have an isometry. In the case in which this parameter takes its maximum value, so we have the maximum possible inhomogeneity for the graph, then we obtain that the isometry condition is satisfied only for sufficiently high values of the edge spins. So what we can deduce from this picture is that the inhomogeneity of the graph is something that favors the isometric character of the corresponding map. Okay, so what I presented so far is something that was contained in the paper I mentioned before. This is a set of results that will appear soon, hopefully. And so this is instead the same kind of technique, but applied to see which is the effect of the bulk entanglement on the boundary. So differently from the previous case in which we consider the graph state and see which kind of channel that state represents. Now we probe the boundary, just the boundary state, and we are interested in see which is the effect of a certain set of bulk correlations present on that state. So the starting, the state we focus on as the following form. So we still have random vertices, the set of links that implement the connectivity pattern, and then we have a choice of intertwiner correlations. So the state, the density matrix is the following. So the difference with respect to the previous case is that now we have the input bulk state, which is considered together with the rest of the graph. So now we want to compute the entropy of a certain region of the boundary to see the effects of the bulk correlation on it. So again, we have that the entropy calculation can be mapped to the evaluation of a partition function for an easy model. The difference is now that the swapping operator only refers to the boundary, so there are no pinning fields for the bulk degrees of freedom, but just for the boundary ones. And the other difference is that now we have a bulk contribution, so the easing action also involves the second order Ranier entropy for the bulk state. In particular, the entropy for the state reduced to the region in which the easing spins point down. This is what can be explicitly seen by performing the trace. Let us first focus on the homogeneous case. Again, we have that the logarithm of the dimension of the link plays the role of inverse easing temperature. And now we have an easing Hamiltonian with the first part, which is a proper easing like Hamiltonian, and then the bulk contribution. Now, we can easily see that the easing part is nothing else that the area of the domain wall separating the spin down and the spin up regions. Why? Because we are so the boundary pinning fields, which are depicted in red in the figure, point down. This means that the easing spins tend to get aligned with them to minimize the energy, because this term is equal to 0 when we have alignment. And so these the set of spins which are close to the A region tend to point down, and the only contribution to the Hamiltonian comes from the misalignment between the easing spins across the domain wall. So this part is just, as I said, the surface, the area of the surface in terms of the number of links which are cut by it. And then we have this bulk contribution. So what we can see from that in the case of small entanglement entropy for the intertwiner, we recover an area law with a bulk correction. So just in the case of it is a 0 or very small, we still have that the dominant term is the minimization of the area of the domain wall. The story is different when the contribution from the intertwiner entanglement entropy is very large. So in this case, the bulk entanglement can strongly modify the behavior of the domain wall. And I'm showing an example which highlights that. So consider the case in which the bulk entanglement is present only in a certain region of the graph that we call omega. So the bulk state is a certain random Q state in this region and a tensor product state outside. So this part does not contribute to the entropy. Then we have that the Arrhenius entropy of the boundary is given by this formula. And to show you a concrete example, here we can see in the case in which there is no bulk entanglement for the bulk, so we have the area law. But in this case, the minimum energy is degenerate. So we have a domain wall with dimension in terms of number of links, a dimension 5 for both the surfaces shown in the figure. Once we turn on the intertwiner correlations, we have that the degeneracy is removed because we have a contribution, which is this term here, a contribution from the bulk. And we can further increase the effect of the bulk by increasing increasing the dimension of the bulk up to the point in which the domain wall is prevented from entering it. Now, in this homogeneous case, the only parameter we can modify is the number of vertices. So in this case, we are increasing the dimension of the bulk with a refinement of bulk vertices within omega. But we can consider in the inhomogeneous case, and in the more generic one, a similar situation, but the increase of the contribution can be from the bulk can be controlled by the dimension of the spins. So in this inhomogeneous case, we can see that the Ising Hamiltonian is slightly more complicated because the interaction between Ising spins and between Ising spins and boundary spins is different for each pair because it's proportional to the corresponding link. And so here we have the interaction strength. And we also in this case, we consider an example, a specific example to highlight the behavior of the boundary respect to the bulk. So we consider a spherical symmetry with a gradient of the edge spins, a radial gradient, so that for each shell the spins increase with the radius of every shell, and we assume that the entanglement among the intertwiners is present only up to a certain radius peak R here. Again, the state is considered to be in a random Q state, so this is the contribution for the entropy. And so what we can see here is that in the case in which there is no bulk entanglement, the condition for the domain wall to fall from a certain shell to the inner one can be easily satisfied, especially for high values for a larger boundary portion. And the other effect that we can see is that once we turn on the intertwiner correlation in a certain disk, in a certain region omega, the domain wall is stopped and is prevented from entering it. So we have a sort of black hole-like region that arises in this case. Okay, so let me summarize what we have seen. So first of all, that every state associated to a spin network graph can be seen as a map from the bulk to the boundary degrees of freedom, and that we can investigate the isometric character of this bulk to boundary map and translate the condition of isometry to that of having a bulk, a reduction to the bulk which maximizes the entropy. And then by exploiting random tensor network techniques, we investigated the holographic character of these maps, and so we have seen that in the case of homogeneous graph made of four-valent vertices, this flow of information from the bulk to the boundary cannot be anisometry. That for a graph with a generic assignment of edge spins, if we increase the inhomogeneity of the spin assignment, this increases the holographic, the isometric character of the map. And then we analyze which is the effect on the boundary of having intertwiner or having quantum correlations, entanglement between the bulk intertwiners. And we have seen that in the case in which this bulk entanglement is small compared to that of the links, we can recover an area law with small corrections that derive from the bulk entanglement entropy, and that if we increase the dimension of the bulk, increasing the number of vertices or increasing the dimension of the intertwiner degrees of freedom thanks to the increasing of the spins, they recouple, then there is the emergence of a region that is like a black hole, just in the sense that the domain wall is prevented from entering it. So because there is no causal structure here, so clearly this characterization can only be at the kinematical level and only in quantum information terms. Now there are several generalization and issues that can be tackled next. I mentioned a few here. So the first point is to generalize the work to include superposition of spins and of different graph states. But then from the we could exploit this technique to characterize a black hole horizon in information theoretic terms. So in terms of flow of information from a bulk to the boundary, and once we have the complete picture of generic states. And I also wanted to mention that thanks to the exploiting of tensor network techniques, we actually have a set of numerical tools from the condensed matter area that would allow to a numerical simulation of phase transition for the boundary entropy and for a number of other quantities we can model through these generalized tensor networks in this quantum gravity context. Okay, thanks everyone. Sorry if I ran out of time.
Thank you very much, Eugenia. So if you have questions. So in the meanwhile, I'd like to ask a question about if we put some dynamics, some Hamiltonian dynamics, like in loop quantum gravity acting on spin networks, where is it going to come in? I mean, how it's going to change, or how do you take it into account?
Well, yeah, the dynamic part, in fact, here would be could be, for example, introduced in the part in which we consider the mapping between channel states, in the sense that in this case, since instead of this tool, which is a sort of dualism between the map and the state, allows us to, in a certain sense, to translate from the dynamical properties of a map, even if there is no dynamics strictly speaking here, to the static properties of a state. So the idea could be to perform the same kind of computation and look at just the static properties of a state, but which is dual to a map that can be a dynamical, that can represent a dynamics, not just, as in this case, a sort of, this is a flow information, but at a kinematical level from the map to the boundary. I would say that this can be a way to generalize this picture to the dynamical one. So trying to so assume that the bulk to boundary map is not just at the kinematic level, but at the dynamic one, and map the dynamical properties of it to static properties of the reduced state.
And and what can you try to do with your? Oh, Simone, you had a question?
Yes, but please finish.
Oh, I just wanted to ask, what did you want to try to do with your definition of a black hole?
Well, the idea is to I mean, this is in terms of just the entropy of a boundary respect to the entropy of a respect to the structure of a bulk. So the idea would be to properly characterize the horizon. So in terms of not just the boundary, but in terms of all kind of information we can. So, for example, try to see if what happens to the mapping of observables from the bulk to the boundary, what happens to the bulk to boundary maps that we investigated in the other context. So the first step would be to connect to some results on typicality that allow to characterize a black hole in terms of sort of ratio between the bulk and the boundary dimension, and so properly characterize which is the threshold that causes a certain region to behave like a black hole. So in this case, we just employ the refinement of vertices or the gradient of spins, but the picture can be generalized to include a more general characterization.
Thank you, Eugenia.
Yeah, so this boundary Hilbert space you use, is it made out of just points, or there's also relations between the points somehow induced from the bulk graph? This wasn't clear to me.
Well, the boundary, so we are the correlation between the boundary edges are the one contained in the graph states. Of course, once we consider random tensor network like this, since we are randomized over the vertex wave function, in a certain sense, we are erasing all the information among the degrees of freedom which are not in the connectivity pattern. So in this case, in this case, we are not considering a certain specific correlation between the edge degrees of freedom. It's just a sort of basic state for the boundary. And we are looking which is the effect of feeding the graph with certain bulk correlations. But the randomization procedure is a sort of acts as eraser of all quantum correlations on the starting graph state.
Okay, but the boundary state is only, of course, there are non-trivial correlations, I understand, but it's only labeled by quantum numbers that live at the nodes, at points. There isn't.
Only labeled, in that case, yes, on the spin projection on the boundary edges, because the only correlations we implemented are among bulk degrees of freedom.
Okay, and so these a priori are like magnetic numbers, right? That you have.
Yeah.
And so when you stressed this connection with the IC model, was it for any spin, or was it because you had in mind spin 1/2?
No, the connection with the Ising model is a different. Let me take no, yeah. So the point is that it's, the Ising spins that arise from the tensor network techniques are just an effect of the having two copies of the spin network graph and then performing this average that makes one copy interacting to the other. So it has nothing to do with the magnetic spins we assume on the boundary. It's just
it has to do with the fact that you're looking at the Reni 2 entropy.
Yeah, exactly. If we would look at either order Rani entropies, we would have not just binary variables, but
and a completely different question, more conceptual. In some of the loop quantum gravity literature, the open spin networks are used to represent matter degrees of freedom. What is your viewpoint on that?
Well, we could, so in this case, the degrees of freedom are understood just, not just as matter degrees of freedom. Actually, this is a technique that can be easily generalized to include the matter degrees of freedom because it's just, so in terms of tensor networks, we would just add links, open boundaries to the basic network, to the underlying network. So in fact, this is something we want to look at, especially for what concerns the black hole like region, because the increasing the dimensionality of the bulk could be done not only in terms in geometric by geometric degrees of freedom, but also matter ones. If we would have additional matter degrees of freedom there, we would have additional interacting Ising spins, and so the possibility to increase correlations in a certain region.
So for the applications of your techniques you have in mind, it is important that these degrees of freedom are understood in some geometric way and not as matter.
No, this is actually completely general. So no, they could be understood in both ways. So the way we are employing them here is not in terms of matter degrees of freedom, but the technique by itself is completely general. Of course, I mean, we can only, if we want to consider matter above a certain graph structure, this is the basic framework we can have. And then other degrees of freedom has to be put on the top of it. So this is, I would say, the basic framework to deal with that. But no, the technique is completely general. In fact, in tensor networks, this is a priori not related to spin networks.
Okay, thank you.
You're welcome.
So if there's no other question, I would like to thank Eugenia for the talk.
Thank you.
Very
James,
interesting
for
talk.
this.
And I'm going to cut the recording.